Imagine thousands of concurrent requests hitting a standard Node.js server simultaneously. The system immediately struggles to process the overwhelming volume of traffic. Node.js runs on the V8 engine, which relies on a single-threaded event loop to handle execution. If that one thread gets locked up processing a heavy synchronous task, every other incoming request is forced to wait in line. When applications attempt to manage caching, memory states, or heavy data processing directly inside that single main thread, the server becomes unresponsive. A single massive file upload can block every other active user. To survive enterprise-level scale, you have to push state and heavy computation out of the node instance, delegating those tasks to external systems using strictly enforced boundaries. Scaling a Node API into a resilient system requires more than clean code. It requires orchestrating a network of asynchronous boundaries to keep the main thread clear. This is the core of the NestJS framework. Using a strict dependency injection container, NestJS allows developers to securely orchestrate external systems without tangling them into the business logic. To maintain this structure, the system first requires rigorous configuration management to handle environment variability. For performance, it must utilize distributed caching and rate limiting to shield the core database. To ensure observability, every request needs to emit structured logs and distributed traces from the moment it enters the system. Finally, background processing must be handled by offloading heavy tasks to dedicated message queues. NestJS provides the module system and dependency management required to scale these four subsystems while keeping the underlying logic maintainable. Pulling environment variables directly from process.env is an unreliable pattern for applications deployed across dev, staging, and production. Reading raw strings at runtime frequently leads to silent failures. NestJS addresses this through the config module. By pairing it with schema validation libraries like Class Validator, the application treats environment variables as strictly validated objects. This animated diagram shows the bootstrap phase. Raw data from a .env file attempts to enter the application, but it first hits a rigid validation boundary created by the config module. This creates a fail-fast mechanism. If a critical variable, like a database URI or a Redis port, is missing or malformed, the validation boundary instantly turns red and halts the boot process before the app can start in a broken state. Once validated, the boundary turns green. The clean, typed configuration object is injected across the entire dependency graph, providing verified credentials to the modules connecting your databases, caches, and APIs. Injecting a centralized configuration service also removes the need to mock raw process.env variables during unit testing. Validating configuration at startup is the first line of defense against production outages caused by malformed credentials. Even with valid configuration, sudden traffic spikes can exhaust a database connection pool, creating latency as queries wait in line. To protect the database, enterprise systems use a distributed caching layer, typically an in-memory store like Redis, to store temporary state. The native NestJS cache module connects to this layer, allowing developers to apply caching behavior directly to the request-response cycle. This flowchart details the standard NestJS request lifecycle. An inbound request moves from the client through middleware, guards, pipes, into the controller, and finally down to the service for the database query. We can physically intercept this request by wrapping a cache interceptor around the route. This places the caching node between the guards and the pipes. When a request hits this interceptor, it pauses and queries the external Redis node to see if the requested data is already in memory. On a cache hit, the interceptor short-circuits the lifecycle.
Redis returns the data, and the flow routes back to the client, bypassing the controller, the service, and the database. This interceptor layer is also the optimal place to implement rate limiting, blocking abusive traffic before it consumes application resources. Placing caching and limiting logic at the application boundary keeps the core business services focused on domain logic, while shielding the database from redundant load. Standard console.log statements are ineffective in highly concurrent systems. They provide no way to isolate a single user's path among thousands of overlapping entries. This image shows structured JSON logging. Instead of a flat string, every log is an object containing timestamps, environment data, and a unique trace identifier. In NestJS, we implement this by replacing the default logger with a library like Winston, instantiated globally to cover the entire application. To track a request across different services, we generate a trace ID. In our flowchart, The request enters the global middleware and is permanently tagged with a unique ID marker. As the tagged request moves through the guards, interceptors, and services, every log emitted at every transition includes that same trace ID. If a failure occurs, developers can query their logs for that ID to reconstruct the exact path and state of the application leading up to the error. NestJS global exception filters catch unhandled errors and append this trace data to the final log before returning a response to the client. Observability must be structurally baked into the request lifecycle. This ensures that every event on the server is part of a traceable, documented journey. Despite caching and observability, the fundamental rule of Node.js remains: you must never block the event loop. Operations like complex report generation or bulk email dispatch are too heavy for the main thread. As said in this video, we must divert these large tasks off the main conduit and onto a secondary track. This secondary track is a message queue, specifically bull-MQ, backed by Redis. This shifts the role of the API. In this diagram, the controller receives a heavy payload. It packages that data into a job object and pushes it to an external queue node instead of executing it. After pushing the job to the queue, the controller sends a 202 accepted status back to the client. The main API thread is instantly freed while the job sits safely in the queue. Separate background worker processes pull those jobs from the queue and execute them independently of the main API flow. This decoupling allows you to scale worker processes on different hardware based on queue depth without impacting the responsiveness of the API. The queue also manages failure. If a job fails, the system retries it with exponential backoff without crashing the application or losing the data. Because the queue tracks job state, the client can pull the API for updates or wait for a webhook to trigger upon completion. Message queues allow the API to function as a traffic director, delegating heavy operations to specialized workers while maintaining immediate availability for incoming traffic. When configuration, caching, observability, and queues work in unison, they form a resilient distributed system. In this macro topology, traffic hits the system. Validated configuration secures connections, while the cache interceptor instantly handles most volume. The remaining traffic is logged with trace IDs, and heavy payloads are shunted to bull-MQ workers, keeping the central API thread clear. Even under extreme load, the V8 event loop remains responsive because we have offloaded state and computation to external services. Transitioning to this architecture is facilitated by the strict module and dependency injection paradigms within NestJS. NestJS provides the structure required to orchestrate these distributed systems, allowing developers to scale their backends with confidence.
Enhance your coding skills with us. Don't forget to subscribe to Code 5 Foot for the latest updates and tutorials.